Andrew Poelstra, Director of Research from Blockstream.
All right, hi everyone. So some of you were at my Bitcoin dev meeting presentation about miniscript a couple days ago, where I managed to spend over 2 hours giving a presentation about this. I think I got this one down to 20 minutes, but no promises. I'll keep an eye on the clock. It was very nice having this scheduled immediately after Andrew's talk about output descriptors, because there's a good transition here. As Andrew mentioned, the way that the Bitcoin Core wallet used to work and still works is this sort of bag of keys things, where you have a whole bunch of elliptic curve keys, and then these are interpreted basically in whatever way happens to be convenient at the time, and this results in kind of a messy user model and potentially weird things like the ability for third parties to manipulate addresses in unexpected ways. So descriptors solve this, basically, by being much more precise about the way that keys are supposed to be used, and also by being more expressive. But as Andrew hinted, there are more ways that descriptors could be expressive, and that brings us into miniscript. There are things like multi-signatures, there are things like various multi-key policies that it would be nice if descriptors could support now that we have some nice engineer-readable representation of things. Okay, so there are a pile of use cases, even for kind of ordinary users. This is not necessarily things like Lightning or complicated protocols or anything where you might need multiple keys. Ordinary users who just want to have multiple redundant hardware wallets, like Stepan was talking about, might want to use multi-signatures. People who might want to have some backup key, some sort of like dead man switch, where if they lose their hotkeys after a time, they can still recover their coins. That's a sensible thing to want to do. That would require a time lock or something. And then these things might also be embedded in some larger scheme. Like you can imagine somebody who wants to do this complicated multi-signature for their own purposes, but then their key, or they are a participant in some larger scheme, like they're in a split custody wallet. Say they've got some counterparty who's going to countersign all of their transactions. Maybe they'd like to do something interesting, and the counterparty hopefully shouldn't have to be decoding weird scripts to understand what the user's doing. Or maybe they're part of a custody set or like a board or somebody for some company that holds a lot of Bitcoin, like Blockstream, say. And they have their own complicated multi-key setup, and then everybody who works at Blockstream has their own weird complicated multi-key thing. Wouldn't it be great if they could all bring their policies to the table and we could just combine those and have some threshold? We say like 3 of 5 people or 8 of 10 or however many we can get. And each one of those individual policies was something complicated. These are the kind of things that are very difficult to do today because we don't have a good way to represent complicated scripts. Okay? So the way that we do represent scripts is through this thing called Bitcoin script. I've been using this word script. What I really am trying to hint at are spending policies here. But the way that it's implemented is this Bitcoin script. And script can do all sorts of cool things. One interesting example is like Peter Todd has some coins out there that can be taken if you can find a hash collision. Okay, so there's one for SHA-1 that's been taken. There are others for SHA-2 and RIPE-MD and stuff, which have not been taken. So that's a cool thing you can do with scripts. But in practice, what people typically do are they use script to check signatures with certain keys. They check for hash preimages for things like atomic swaps or lightning HTLCs, and they check time locks for things like these dead man switches or like backouts or claim or refund constructions or something. And then they compose these in various ways called monotone functions. A monotone function is just ands and ors and thresholds, just like putting things together through some tree of ands and ors and thresholds. Okay. So conceptually, these monotone functions of various spending conditions these are like spending policies. They're not really scripts. They're not really programs that you're running. And so you could imagine if Bitcoin were differently designed, that you could directly encode a list of spending policies. And I've given an example here in a suggestively descriptor-like format here. You could imagine having some sort of multi-signature policy. We've got these 3 keys, A, B, and C. We've got some sort of 1,000-block timeout, and you put these together in that way. And wouldn't it be cool if you could put that into a descriptor? But then the question becomes, how do you map something sensible looking like that into Bitcoin script? And that's where miniscript is going to come in. So the idea behind miniscript is that we can take a policy like that. We have all these components, keys, and hashes, and so forth. And we just map these directly into script. We have these script templates, which when executed, do the required check kind of thing. And you also have these script templates that will work as ands or ors. So you can like compose these. You can take like a template that's got a couple gaps in them, just fill in other script components, and basically almost like an encoding of, or literally an encoding of the spending policies in Bitcoin script. And it's kind of cool because there's conceptually two ways to read this. You can read this as this tree of ands and ors and stuff, or you can read this as a program to be executed on the Bitcoin blockchain. Okay? But to summarize the situation that I'm describing, script works by manipulating these opaque blobs of data. It's a very low-level stack machine. You give it a bunch of objects. Some of them represent Booleans. Some of them represent signatures. Some represent public keys or hashes. Some represent numbers that you can add together. You can do various operations on them. It's really not thinking in terms of spending policies. And the difficulty with the current situation is exactly this, that the script model is this low-level stack machine that doesn't have any obvious mapping at all to the model that I'm trying to describe, where you've got a collection of different spending conditions, okay? So, but miniscript, as we'll see, does match this user model, all right? So let me kind of summarize the problems with script as I see them, or a giant list of many problems that I see with script, real quick. When you're in the stack-based low-level opcode model, it's difficult to argue that your script is correct, that it's actually going to do what you expect. It's difficult to argue that it's secure, meaning it won't do what you don't expect. It's difficult to argue about malleability, and that's something I'll talk about in a couple slides. If you're a wallet implementer, you run into problems with fee estimation. It's difficult to estimate how large a witness might be when you're actually satisfying a given script. It's difficult to know, if you've got multiple parties involved, which public keys require signatures and how many signatures you need. And do you require hash locks, and do you require a certain time lock to be signed, and so forth. And even if you can figure out that data, figuring out how to assemble it into a witness is non-trivial, because Bitcoin script has a lot of different opcodes that require different things in different orders and in different formats. So if you were trying to write software that could work with arbitrary scripts, you've got quite a difficult program analysis problem on your hands. Okay? So these problems with script, though, directly translate into problems for designing something like miniscript, right? The idea is I can just encode my spending policies as scripts. Well, scripts have these problems in the miniscripts. Then in designing these fragments, these templates, I'm going to have these problems. So one is that there's many ways to write every fragment, right? If I'm trying to do a public key check, I can use the checksig operator. I can use the checksig verify operator, which has slightly different semantics. I can use the check multisig operator and just like throw a single public key in there or something weird like that. So there are three ways to write, say, a pub key check. The check multisig one is obviously inefficient. There's no reason to do that, but the other two might be usable in different contexts. It's hard to compose these fragments. The checksig operator, if it succeeds, will put a 1 on the stack. If it fails, it will put a 0 on the stack. Checksig verify, if it succeeds, will put nothing on the stack. And if it fails, it will abort the script. So if I'm trying to write a script fragment that represents like a Boolean AND or a Boolean OR, I need to consider that for some things I plug in, I'll have a 1 or 0 sitting around, and for other things I plug in, I won't. And so maybe I need different kinds of AND and OR fragments that can handle these different possibilities. So there's kind of a design problem here, and there's an analysis problem in making sure that the actual composition of fragments that a user comes up with is something sensible. And then another constraint is I can't just like throw away every fragment except for 1 or something. I can't just do something silly and inefficient and simple, because cost is really critical here. Every byte matters here, I guess, as Monty Python says. Every byte is precious on Bitcoin. And so, yeah, there's a few chuckles. Users really care about the size of their script pub keys. They care about the size of the witnesses that they produce to spend their coins. And those are actually two different things. And actually, when they're composing things, they may care about the size of the witness if they're not satisfying something. If you've got like an OR of 2 different branches, maybe you satisfy one but dissatisfy the other. So there are all these different cost dimensions when considering the size of fragments. And when you're designing a miniscript, you need to consider for every fragment how likely it is to actually be satisfied, and how likely it is to be dissatisfied, and how likely it is to just be skipped completely over, like if it's in an if branch that doesn't get called. And so this means that there are trade-offs. You can't just pick one fragment that's obviously the best. And even if you know what your policy looks like, there's not one fragment that's obviously the best. You really need to support all these different fragments, and you need a way for the user to verify that what they're doing is not only sensible and not only efficient, but actually the most efficient thing for the specific use case that they're considering. Okay. And then a final point on this slide is just that actually getting an optimal script might involve some really kind of funky things where, like, if you see the same public key occur twice, then maybe you want to like rearrange it so it only occurs once, and you completely restructure what your predicate looks like. That's just out of scope for miniscript. Doing like whole program optimization type things like this would be cool and in theory is possible, but it breaks this nice simple user model where you've got a tree of spending policies, a tree of spending conditions, and you produce a policy that way. And if we were doing too much, like any advanced manipulation on these things, then we would lose that simple engineer-readable, easy to reason about, easy to check consistency kind of properties. Okay. And then let's go into malleability. So beyond thinking about correctness, which in some sense is a straightforward engineering problem, and about optimality, which is also in some sense just engineering, we have this issue of malleability. This was a really hot word before SegWit was around, because, well, first of all, what malleability is the ability for some third party, given a Bitcoin transaction, to replace the witnesses with some other witnesses that are also valid. So you get a different transaction that still does exactly the same thing. It's still a valid transaction, but it's different in some way. Before SegWit, this was really serious because the witnesses would go into the transaction ID, and so if you were chaining multiple off-chain transactions, you would actually just, like, this third party would break the whole chain, and you were in a lot of trouble. Post-SegWit, malleability is still a thing. It's no longer like a protocol breaking thing, but it is an efficiency thing in two big ways. One is that it can affect transaction propagation properties. If somebody changes out a witness, and some nodes have seen a transaction with one witness and others see a transaction with another witness, one of those is going to get into a block, and this can interfere with compact block reconciliation. Like, at some point, you actually do need the full witness and stuff, and if your node is surprised by what the witness in the blockchain turns out to be, that's an inefficiency for the network. So it's not as bad for the network. And then from a user perspective, if there's a potential to replace a witness with a larger witness, that means that your transaction, as it hits the network, is larger than the transaction that you created. And so the fee rate you set is lower, the fee rate that the network sees is lower than the fee rate you set. So now you are surprised by your transaction having a lower priority than you wanted to. And this is actually potentially a security issue, because it means that your transaction might not propagate when you expected it to, or it might not be accepted into people's mempool when you expected it would be. Okay? So to make the task of designing miniscript tractable, we set a few sort of design rules here, which I've more or less already said. The first is, that we're going to assume the standard Bitcoin Core mempool policy rules. Okay, this is standardness is the term we used to use. The reason we do this is that there are a lot of anti-malleability things in Core's policy rules that are not in Bitcoin's consensus. So one prominent example of this is there's an if opcode in Bitcoin. If you give it a 1, it will do the thing. If you give it a 0, it will not do the thing. There are actually many, many ways to encode 1 or truthiness in Bitcoin. There are many, many ways to encode 0. And so if you have a policy, or if you have a script that's using this op-if, and you provide a 0 or 1 in your witness, in principle, some third party could change that 0 into like a 0 that's like 20 zeros in a row. Or they could change your 1 into any non-zero value, or something like that, and then make your transaction bigger, and you're in trouble. You can prevent this. You can make the transaction invalid in this case by using this trick. You use op size followed by op equal verify that I've mentioned here. And this is just like the one little bit of Bitcoin script that I'm going to throw in here. Size equal verify is a really cute trick. So size takes this literally puts the size of your topmost stack element onto the stack. Equal verify checks that two things are equal. So what size equal verify does is if your top element on the stack is equal to its own bit size, that's great. If it's not, it will fail the transaction. And as it turns out in Bitcoin script, there are only two values that are equal to their own size, and that's 0, which is the empty string, which has size 0, and that's 1, which is a 1 byte, just 1, which of course has size 1. So that's kind of cool. So we could put size equal verify in front of every single if, and we could also put extra validity checks and length checks in front of all of our signature checks, for example. And there are a bunch of other sort of guards that we could put into all of our script fragments. But we don't want to do that because we're wasting bytes there. And in practice, this is not really an issue because the network is so overwhelmingly enforcing these policy rules that really only miners could exploit this kind of malleability. And miners already have the ability to mess with transactions. If miners want to hurt network propagation, you know, they can just like produce a whole bunch of transactions that no one has seen before and stuff blocks full of these. And now compact blocks doesn't work, kind of thing. Miners already have the ability. The problem with malleability are already things that miners can do. So we're just going to stick with policy rules. As I mentioned, we're not going to try any common sub-expression elimination. We're not going to try to manipulate our program. We're not going to try to rearrange things. First of all, this is very difficult in general to find the optimal encoding of a program. Secondly, it breaks analyzability. And then also, finally, we're going to assume, for the purpose of reasoning about malleability, which is something we do in miniscript, that I'll kind of touch on but not go into too much detail. For the purpose of automatically reasoning about malleability, we're going to assume that people's keys are not reused within a specific script. And the reason for this is that if somebody uses the same key twice, then if they sign in one branch, where they sign with this key in one branch, a third party could see that signature and copy it and use it in a different branch. And this actually potentially introduces a malleability vector where otherwise there wouldn't be one. And this is very difficult to reason about in automated ways. Like, you really gotta know which branches are disjoint from other branches, and in general, it seems like an intractable problem. We also assume no key reuse for the purpose of fee estimation. This appears in some edge cases when you're thinking about how to estimate witness size. And again, we're just going to throw that away for the purpose of having something that we can describe and that we can deploy. Okay. And then the final design, or big design thing in miniscript that we are forced into is to separate out this notion of the policy language, which is something like I showed you several slides ago, where you've got these ands and ors and so forth, from miniscript itself. And the idea is the policy language is kind of a high level. That's the engineer, that's maybe even a user-readable thing. It directly describes which spending conditions are available and in what combinations. Okay? And in these policies, we also allow labeling different branches with different probabilities for certain branches being taken. Okay? And this allows us to take a policy, compile it down to a miniscript, and make choices about which specific script fragments we want to use based on the likelihood of certain branches being taken. So we get a lot of optimization ability here. So we have this policy language, kind of high level. This is distinct, but very similar to miniscript itself, which I'm going to show you in the next couple of slides. Miniscript really does directly correspond to Bitcoin script. It is actually an alternate encoding of a subset of Bitcoin script, where this encoding is clearly a tree of ands and ors and thresholds. Pardon? Did somebody say something to me? I'm sorry, there's a lot of noise behind me. Yeah. Okay, cool. No worries. So we have miniscript itself, which really is this re-encoding of script. And the difference between miniscript and the policy language is, first of all, there's no probabilities in the script. And secondly, in the miniscript form, cool. In miniscript, we explicitly label which fragments we're using in all cases when there are multiple alternates. Okay. So let me show you what this looks like. So here's an example of a policy. You see, rather than writing it in the nice string descriptor format, I have the ability to draw these nice pictures. So this is a cool thing about miniscript that you can't do with regular scripts, because conceptually what I've got is this tree of objects, right? Rather than having a bunch of instructions for a stack machine. So I get this nice format. So here's a policy. You can see I've got 4 keys going around. I've got some sort of hash preimage. I've got a time lock. Yep. And if there's various kinds of analysis that I might want to do on this policy. Like say I am the owner of public key 4, okay, off in the right there. And my job is to be a countersigner. I don't really care what else is going on here. What I want to know is, can this script be spent without my permission, without me signing off on it? And or after the coins have been sitting still for like 1,000 blocks, maybe I'm willing to back off. And so I can easily go through this and say, well, do there exist any ways to spend this where my key does not appear? So let's go through all of the spending possibilities. The top level, I've got this and, so both of these need to happen, okay? On the right-hand side here, I've got an and, so both of these need to happen. So the only way to spend these coins, I can immediately visually see, is if both of these branches are satisfied. And I can see that one of them is exactly the policy that I want. So I know without a doubt that there's no secret way these coins can be spent out from my control, even though I didn't even look at most of the script. All I did was just run through the branches and just check that there existed one in every possible spending path where my key was involved, or this alternate timeout, okay? Here's what a miniscript looks like, okay? So these are actually almost the same picture. It's taken a moment to load, so it's less dramatic. But you can see the difference here is that in miniscript, I've labeled all the ands and ors and things so with specifically which script fragment I want to use. I've also labeled these as these B's and V's, and there's actually K's and W's. These represent types, which I'm not going to go into in this talk. But miniscript has a type system that allows automatic verification of correctness, okay? And then I've also got these C's, these VC's, and JV's and stuff. What these represent are script fragments that don't really have any semantic meaning, but they allow me to encode things in a more efficient way. So like V, for example, means you add a op verify at the end of something, which turns a 1-0 result, like what checksig does, into a pass-fail result, like what checksig verify does. So V means put a verify on it. J is this weird wrapper where we look to see whether or not the user has given us 0. If the user has given us 0, then we just skip over whatever we're wrapping. If they give us a non-0, we pass that as the input to the fragment. So the reason we do this is for a hash preimage, we want to give the user the option either to provide a valid hash preimage or to provide the byte string 0, which means just skip over this, just like fail to check, okay? And this J wrapper gives us exactly those semantics. So you can see that has nothing to do with the policy, but it is clearly important for actually encoding things as script, okay? And at the bottom here, I've got the actual Bitcoin script in opcodes there. That's what it looks like, okay? For time reasons, I'm gonna skip over this slide, but basically, one of Andrew's projects is PSBT, which is a unsigned transaction wallet interchange format. Miniscript is designed to work with PSBT. They both make each other more powerful. There's some very generic multi-wallet tooling that we can write using the 1-2 punch of miniscript and PSBT. That's all that I'm gonna say here. So let me quickly advertise for my workshop, and then I'll wrap up. So tomorrow morning, I'm doing a workshop, 9:30 to 12:30. Unlike the other workshops here, this is not going to be super programming focused. The reason being that my miniscript library is written in the Rust programming language, and I don't think it's reasonable to expect people to either already know Rust or to learn it in the next couple of days, because it has a very high learning curve, famously. So, and there is a Python implementation that James Chang wrote, but I think it's not quite finished as a PR to Bitcoin Core as part of the Python test framework. But it's not quite finished, and I haven't looked over it, and I don't really know how to use it. So that would be the good thing to use for a workshop, but we don't have access to it. So instead, I'm going to do something a little bit more theoretical. We're basically going to go through a lot of the weird oddities in Bitcoin script. Maybe we'll look at interpreter.cpp, which is one of the weirdest files in Bitcoin Core, one of the oldest files in Bitcoin Core, and see some of the weird things that the script interpreter does that might confound various kind of analysis. And we'll look in more depth at things like correctness and malleability and surprising footguns that you encounter when working with script. And even when working with miniscript, there are surprising things that sometimes the type system, the miniscript type system can catch for you, but nonetheless, they're often non-obvious and subtle things. And actually, over the course of development, I often would try to do weird things with miniscript, and my code would refuse to sign for transactions, or it would reject this somehow. And I think like the code is broken, but then when I traced through the way that it was failing, in fact, it was showing me that there was some malleability vector in what I was trying to do. And like there was an actual attack there that I had not considered. So it's really cool. It's really cool that we can do this in an automated way, because this is really subtle stuff and really foot gunny in non-obvious ways. So to wrap up, there's this thing called miniscript. It makes spending policies, as encoded in Bitcoin script, human readable, let's say engineer readable. I like Andrew's term. And machine analyzable. We can do all sorts of cool things. In particular, things like constructing witnesses, determining what keys are required, estimating witness size, even under certain constraints. These become tractable, and in fact, we can do this in a very generic way, where somebody like me could write some code that does this, and then everyone can just use it. And we're no longer reinventing the wheel for every single individual weird policy. Okay? And you also get this composability thing that I mentioned way back at the beginning of the talk. If you've got some larger miniscript, as we saw with the picture, I can take some little fragment that I care about for my purposes and not really care about what the other participants are doing as long as the overall script is using my policy in the way that I want it to. So we get this composability where I can participate in custodying the keys, the coins that Blockstream controls, say, and I show up to the table with like some crazy multi-signature time lock, whatever thing, and all everyone else needs to know is like, that's me. Somehow that big blob is me, and they know that I haven't somehow backdoored it by doing this complicated thing. And all I need to know is that I'm contributing, that actually you can't move the coin without me or some large number of people. Okay? So there we go. I'll go into this in a fair bit more detail tomorrow morning, and thank you all for listening. Questions? Questions? Comments?
So you were saying that there was a problem with public key reuse. Have you thought about using the very non-famous code separator operator, which allow you to really use only one public key for one person, but sign a specific branch of your script?
This is a really cool question. So the question is about using opcode separator, which is this obscure opcode that lets you basically tag what you're signing in a bit of a technical way, so that a signature for one part of your script can't be reused for a signature in another part of your script. And actually, so first off, this is a little bit inefficient. We're adding extra bytes by sticking these opcode separators in places, and some users maybe don't care about this. But secondly, this actually doesn't cover all the cases that we might care about for kind of technical reasons that I can maybe go into tomorrow. But you can imagine like a threshold policy where you have 3 of 5 participants, say. And so there are 5 choose 3 different ways that you can spend this. And you can imagine like one person signs using like the first 3 signers, and then somebody changes it to use the last 3. And so now the middle signer is in both cases. In whatever. So the middle signer is in both cases. But opcode separator, because it only appears once on that key, won't be able to detect this kind of change of witness. And so in that example, this probably doesn't matter because this is not an example of key reuse. But you can imagine a threshold policy that's more complicated. You can imagine like a threshold of thresholds or something more elaborate where this does actually matter. And I have a few examples of these, just not in my head right now.
When you talk about the J, you said that perhaps the user wants the script to fail, but what would he want that? Then just don't send the transaction, no? What?
Yeah, so you never want the whole script to fail. That's a good point. But you may want some specific subsets of your script to fail. So if you have like an OR, so one way that you can do an OR in Bitcoin is you can run a script fragment. You can store the result. It will be 0 or 1. Just throw it on the alt stack, say. Then you run another fragment, and you store that 0 or 1. Then you pull the 2 results out, and you run the bool OR operation on that, okay? So the expectation is that whichever branch the user takes, they're going to fail one of the 2 things and succeed the other one. And so and then this may actually be more efficient than doing it other ways using like opverify or something like this. And so in that case, you have a subset of your script that you do actually want to be able to fail, because you want it to put a 0 on the stack that you then run through bool OR to get a 1 and pass the larger script. That's why. Whenever you have conditionals is why you might want to fail stuff.
So Andrew Choud said in the previous talk that output script descriptors describe everything you need to solve them. So does that mean there's redundancy between descriptors and miniscript currently as the design?
No, so there's not redundancy. So What output descriptors describe is where do you put the witnesses. Like if you have a PKH or something, you just throw a signature into your script sig. If you're using SegWit, you put your witnesses in the witness field. If you're not using SegWit, you put it in the script sig, that kind of stuff. What miniscript describes is how you actually construct those witnesses in the first place. So they actually complement each other. So output descriptors, as implemented or as on the immediate roadmap for core, actually don't support all of these cool advanced things that miniscript does. They only support, I think, like basic multi-sigs and then all the different ways that you can do single signer keys. So what miniscript gets you is the ability to do way more stuff with output descriptors. But the two parts that they do are actually disjoint, so they're complementary.
I think that's all we've got
Oh,
time for.
okay.
So
Yeah,
thank you very much.
I'll be around. Thanks.
All right. Awesome. Thanks. I'll get the, thanks, man. I'll grab the, thanks. Awesome. All right, thanks very much. Andrew has a way of making these really complex things broken down into ways that we can understand, so great work there. I really enjoyed that.